Good afternoon, everyone, and I would like to welcome to this new appointment of the 40 Under 40 lecture series of Combustion. It's my great pleasure to introduce today Dr. Tim Franken, who is a research group leader for the Young Investigator Group Process Optimization of Power to X Power Systems at the Energy Innovation Center in Cottbus. I will talk more about this center. He also PhD in mechanical engineering from the Brandenburg University of Technology in Cottbus, Senftenberg in Germany, where he has specialized in stochastic reactor modeling and multi-criteria optimization with 10 years of experience in the field. Dr. Franken has published his research findings in various international peer-reviewed journals and in international conferences, and I'm very happy that today he will talk about advancements in carbon-free energy storage, discussing research in COX-based catalyst and oxyfuel combustion. So thank you again, Tim, for having accepted the invitation, and I give you the floor for the presentation.
Thank you very much for the kind introduction, and welcome everybody for our today's seminar. So since Professor Parente already introduced the title quite nicely, so I will directly proceed. I try to proceed to the outline of today's presentation. So our plan for today is separated in 6 sections. I first would like to introduce the Energy Innovation Center and the Energy Storage and Conversion Lab, where we conduct the research I'm going to present today. Then I would like to outline our power to X to power energy system demonstrator that we are currently building up here at the site in Cottbus. And with 4 and 5, I introduce like 2 major research topics of the lab. My colleague Fabian Racho is also today in the meeting, and like together we are working on topics for sodium oxide catalyst development for methane synthesis, and like I'm especially working on the topic on oxyfuel combustion for heat and power generation. Okay, let's start with the introduction of the Energy Innovation Center so that you all get an overview of what we're doing here. So our Energy Innovation Center is situated in Cottbus, and I assume most of you will not know where that is situated. So we are in East Germany, pretty much like half between Berlin and Dresden. And we are pretty close to the Polish border. It's like 20 kilometers from this place. And historically, like our region where we're living is called Lusatia, and it is like a coal mining area. So when you look here at the satellite picture, you see here the mining sites around Cottbus and Senftenberg, which is like a small city in the south of Cottbus. And so with the decision that we are phasing out coal energy until 2038, that actually puts a lot of like pressure here in like what to do in the future. So, and the idea is like to establish like energy research and technology development, since like we want to keep energy as a focus point, but we want to put the focus more in a direction of renewable power generation, hydrogen production involving like electrolysis, and power to X applications. So one big topic here in the region, also in Brandenburg in general, is the topic of power to liquid as a new technology to produce like e-kerosene for airplanes, for example. So like this whole air traffic and air propulsion system is also a big topic here in this area. So yeah, in order to support this transition to like new energy technologies, like we decided to found the Energy Innovation Center so that it can serve as an engine for the structural change here in Lusatia. And the center was founded in August 2022. There was already some time before, which took planning and preparation. And we were quite happy that then finally we could start. And The focus within the Energy Innovation Center is like we have 6 different labs, which are covering like a broad range of energy economics and technology. And I will outline like the 6 labs shortly, so to give you an idea about that. So one topic we are looking in is in the energy economics lab, like how does the future energy market with renewable energy, with hydrogen technology look like? And what tools have to be developed so it can be efficiently controlled and steered. Other questions are on the acceptance on new energy technologies. And here the colleagues are using virtual reality caves where they can basically have virtually the new power plant presented, and then they can investigate the impact on the acceptance of like the society on the people living close by, and so they can better understand how to improve the acceptance. The energy storage and conversion lab, I will talk about that more later, so I will not spend time on this slide to explain it. The third group, the scientific computing lab, is dealing with questions on multi-energy system modeling. So they develop mathematical algorithms, optimization algorithms, stochastic algorithms, which can be used in order to model these kind of energy systems. They're doing aerodynamic investigations of wind power plants or heat transfer investigations of heat pumps, for example. The fourth group is also quite important. Their focus point is, so like if we increase the amount of renewable energy like wind power and solar power in the future even more, we have to have an efficient technology to actually incorporate it in our grids. So like they are looking into the AC-DC converters, which take some efficiency of our process. So there are some losses involved, and yeah, they are developing systems which should be more efficient. And they're also developing systems which are suitable for the large scale, like for the gigawatt applications. The fifth group is then focusing actually on the grid itself. So questions here is like, if the energy network in the future is becoming more distributed with smaller power plants, and how can we manage that effectively in the future? So the approach of smart grid is a focus point here in order to have like a virtual central power plant that can be effectively controlled by like a central algorithm. And the last group is focusing on control systems and cybersecurity. So control is, of course, involved in all the different aspects and have a major impact on the performance. And cybersecurity motivation here is that with increasing connectivity of energy technology in the future, there's also an increasing vulnerability against like hacker attacks, for example. So motivation here is how we can make those kind of energy systems safe by using artificial intelligence and honeypot technology. And a third aspect of this lab is this kind of how do we deal with user data? So we have this kind of smart meters in home, and companies who are operating the grid and energy systems would like to use that data to optimize their products and processes. But there's, of course, like a collision with the privacy of the person. So like one research aspect in this group is then as well, how can we like make this data anonymous so that we do not hurt the privacy of the people, but still we can use the data effectively for the energy company in order to use it for optimizing of the processes. Yeah, so the goals and research of the Energy Innovation Center, you find on the right side in the box one more time a summary of the research, which I just explained. On the left side, our goals, we have 3 major goals. The first one is we want to support the transformation of the energy sector, as I already explained. before, and we still want to keep like the regional impact. So we also want to be a contact point for the small, medium-sized enterprises and companies from that region to research products, to develop their products, to be a scientific partner. The second objective is establishing a technology leadership in science and industry, and in the long term securing that leadership. This also involves like establishing fundamental research on an excellence level. And the last goal is like the like creating some kind of mindset of innovation and startup activity here in Lusatia, so that there is a high motivation in developing patents, but also like to bring such kind of ideas into products, forming small startups and small companies who are then becoming participants and actors in the energy market in the future. So we are funded by the public government, like by the German government, to hire 70 scientists who work in our group and technicians. We have some industrial partners who perform this research together with us. So like that we can get this whole center running and established. So currently we are in the build-up phase of this center. And yeah, in the next step, that would be then actually going towards like establishing and continuing that research. Okay, let's come to the energy storage and conversion lab, and I give a little bit details about what we are doing. So we are a consortium of 4 chairs who are working on different aspects of a power-to-X to power energy storage. The first aspect is we are working on the anion exchange membrane electrolysis, which is some new type of electrolyzer, with the motivation that this system combines the advantage of high efficiency of a PEM electrolysis with the cheapness of alkaline electrolysis. So therefore, we obtain a novel electrolysis system which can produce larger amounts of hydrogen at a lower amount of cost. That's the motivation. And the second research topic, which is one of the focus points of the today's seminar presentation, is methane and methanol synthesis. Here, our motivation and goal is to develop novel catalysts in order to improve the efficiencies of the synthesis process, and also developing reactor prototypes for the applications, for the real applications. Another topic on electrolysis is the high or the ultra high pressure electrolysis, with the goal to develop the direct electrochemical conversion of water to hydrogen at 700 bar pressure. This requires overcoming issues with cross-flow effects, also some material characterization, and developing on new electrolyzer designs or cell designs which can like bear these high forces occurring at these high pressures. And the last aspect is basically combining all the knowledge of the different fields, adding to that as well the topic of oxyfuel, CHP, combined heat and power production, and developing a chemical energy storage, which can be used in order to integrate renewable energy much more effectively in our energy market. The topics I'm going to present today is not like only my own research, and it's a result of a group, and therefore I would also like to acknowledge this contribution on the research and that I'm going to present to you today. And therefore, let's start with the actual topic. So first off, I would like to introduce the idea of the power-to-X to power energy storage demonstrator that we are planning to build up for investigating this technology and performing the research. I assume most of you are familiar with this power-to-X to power system, but nevertheless, I would like shortly introduce the concept behind it. So with power to X, which we already know for some while, since the beginning of the 2000s, it's a huge topic. And the motivation is that we are using renewable power in order to produce green hydrogen using electrolysis plants. And with the green hydrogen and CO2 from as a waste product, we can then actually in a synthesis process produce a synthetic fuel. The X stands, of course, for different kinds of outputs, like could be focused on chemicals, could be focused on liquid fuels, on gaseous fuels. So it's just a placeholder. Two examples we can give, and which are also important to us, is the power to gas process with the production of synthetic methane. And a second example is the power to liquid process with the production of synthetic methanol or paraffins or ammonia. Then when we go the next step, we have the X2 power process, which is then taking the chemical energy carrier and convert it into electricity and heat. And examples could be like a fuel cell process as like the reverse process of an electrolyzer, could be mild combustion burners. So depending on your application, maybe that is better suitable. And microgas turbines and internal combustion engines would be other examples, while the internal combustion engine is currently in the focus point of our research. So here is the concept of this power to X to power energy system. So like as the backbone, we have the electrolysis system, which is supplied with electric power from renewable energy systems, and we have the water. And we're producing the hydrogen and the oxygen, which can be stored. And in the next step, we can utilize the hydrogen together with CO2 to produce a synthetic hydrocarbon. For example, via the methane synthesis process, we would produce a methane, and we can like extract the methane from our exhaust gas mixture by just condensing the water and store the methane as our chemical energy carrier. So that is then the power to X part. When we go up, that would be the methanol synthesis process, which also is a power to X part. But today I will not focus so much on that topic. Nevertheless, I want to mention that that is also like a research focus in our group. So the methanol synthesis process, actually, like we're using also hydrogen and the CO2. We have our methanol synthesis reactor, and we create a mixture of methanol and water and some like intermediate gases. So usually like the conversion rate is not that high compared to the Sabatier reactor, like which is used here for the methane synthesis. So usually like you have a circulation in order to increase the yield of methanol of such a reactor. Yeah, with a flash reactor, you can then separate the gases from the liquids, and then you have the mixture of methanol and water going into a distillation process, where you can then, due to the different dew points, separate the water and the methanol, and you can obtain your pure methanol and use it as a chemical energy storage. The next step is you using the chemical energy carrier in order to convert electricity or convert it into electricity and heat, which we do via a gas engine process. So means we are burning the fuel together with the oxygen from the electrolysis device, and yeah, then we would ideally obtain an exhaust that's only consisting of CO2 and H2O, and we can condense the water, and we can store our pure CO2 in a storage and use it for our synthesis process, or for example, as a dilution for the gas engine to control the temperature. This is what we then denote as the X2 power process. So looking into the power to gas process, there are like three main reactions we can identify. So like first, like the CO2 methanation, you have CO2 and H2 as adducts. The stoichiometric ratio is like 1 mole of CO2 and 4 moles of hydrogen. The whole process is exothermic, so we are releasing heat in that process, and we're producing methane and H2O. Via the water-gas shift reaction, there can be conversion of CO2 to CO, which is also in this forward reaction is the exothermic process, while the reverse reaction would be like an endothermic reaction. So you can have the partially oxidize the CO, and together with the hydrogen, you can as well have a reaction which forms methane and water, and is also like a slight exothermic reaction. Usually this reaction is conducted at 10 to 20 bar pressure with a temperature of 300 to 350 degrees Celsius. And typical catalysts are nickel for methane synthesis on aluminum oxide as a carrier material. For the development of our prototype or of our demonstrator, we are going to build up a Sabatier reactor for a more real application. Our idea is a multi-channel reactor. So you see here the different pipes which will be filled with the catalytic material. And this is then put into a casing, and we have two caps from each side in order to close and have actually the gas inlet and the gas outlet. Furthermore, here on the side of the casing, we have two openings, which are then used for the cooling of the reactor. Since it's exothermic, it will temperature will increase over time. So in order to avoid formation of hot spots in the system, we have to cool it. And first approach would be cooling by air. So we would have the cool air going inside. Then we will basically guide it along our reactor pipes, and the heated up air is taken out of the system so that we can make sure that we have some homogeneous temperature distribution in our system. Further developments are regarding, is it better to have a one-stage or a two-stage system? Advantage with a two-stage system would be the possibility of intercooling, so that we have a better control on the system temperature and therefore a much more stable and efficient operation of the system. For the Oxyfuel CHP part of our our demonstrator, we are currently converting our methane air combustion plant into the Oxyfuel operation. We are doing the gas supply via a bottle system, and we will further extend that system with a gas mixing station, which allows us to prepare different oxygen, CO2, and methane mixtures, which we can investigate in our power plant. We are integrating freely programmable control units, so we can actually change the operating conditions accordingly. So changing spark timing, changing engine speed, so we can optimize the operation of the power plant. For analytics, we having respective measurement systems for pressure, temperature, and exhaust analytics. Additionally, we can connect a fast Fourier infrared spectroscopy in order to analyze multiple components in the exhaust gas. For the CO2 separation, we are planning to build in a cooling trap so that we condense the water from the exhaust stream, and then we can recirculate the CO2 into a storage device and use it either for the Sabatier reactor or for dilution of the gas engine. So the whole system is on a small scale. So we are in the low kilowatt power range. The first demonstrator we are building up is just circulating the methane in the system and the CO2, while the hydrogen and the oxygen will be supplied by bottles. As a next step, of course, we would implement an electrolysis system. So there we have multiple options. Either we implement an electrolysis system directly on site, or we connecting our demonstrator plant with our hydrogen electrolyzer on the campus and using the hydrogen produced there for our system. Yeah, overall, the whole demonstrator is like in the first version equipped with the Oxyfuel power plant, a fixed bed reactor, a CO2 storage and a methane storage system, a gas mixing station for preparing the inlet gas of the Oxyfuel engine, and then respective measurement equipment. And the information we want to gain with the demonstrator is better understanding of the coupled system of the Oxyfuel and the fixed bed reactor. Also, like investigating energy balances and storage performance, and yeah, basically evaluating and determining the feasibility of the Power-to-X to power energy storage. Intention is that such kind of storage can be used as a seasonal storage, where you can produce hydrogen in the summertime and convert it via the synthesis process into methane, and you can store it in a large tank. And then during the colder times, you can then actually activate the Oxyfuel process and use the stored methane and the stored oxygen in order to produce power and heat. Okay, now I will step a little bit more into detail into the developments on cerium oxide catalysts in our ESC Catalyst lab, and what current investigations are ongoing. First off, I would like to give a short overview about the different sections we are working on in the ESC Catalyst lab. So the first section is dealing with the development of the cerium oxide based catalyst and support. So in our lab, we are capable of preparing our own catalyst materials and then actually adhere it to the support material. We can create nanopowders and spheres or pellets, so that we can also have different kind of shapes of the catalyst material. And the second part, we can characterize the catalytic material using spectroscopy and macroscopic measurements devices. And currently we are building up a near ambient pressure XPS device in the lab, so that we can do surface characterization under more realistic conditions. More realistic means that normally the XPS measurement is conducted under a vacuum pressure of around 1e-10 bar. And with the NAP XPS process, actually this investigation can be conducted at a pressure of 1 millibar. It's still a difference to the 10 bar, which we're actually using in the real Sabatier reactor, but it's much closer and therefore should give us much better insight what's happening on the surface. The third part is investigation of the catalysts under more realistic conditions. So therefore we have a reactor test, or a catalyst test bench, which consists of a pipe which can be filled with catalyst material, and then we can investigate it under different pressure, temperature, and mixture conditions. And with the energy system demonstrator, we would actually have then a real reactor, or a reactor which is for the real application, and can then also investigate it, including the heat management, for example, of such a reactor. Yeah, and the last goal or part is that with the information from the experimental campaigns, we want to understand the reaction mechanisms related to the catalytic material. We want to derive the reaction mechanism and use it in numerical model development, so that we can also simulate the process, and we can optimize the process using numerical tools. Okay, so why do we investigate ceria? And so motivation comes a little bit from former investigations we did from after treatment systems. Like in gasoline engines, we have the three-way catalyst, which is used for conversion of CO, hydrocarbons, and nitrogen oxides. And there we use cerium oxide as oxygen storage. So because like the three-way catalyst is usually not operated like as at a fixed air fuel ratio, but we have like a high frequent signal of slightly lean to slightly rich mixtures, so that in the different phases we can actually convert either our CO and hydrocarbons or our nitrogen oxides, so that we can reduce like actually 3 components in one device. So, and the cerium oxide is therefore used to store the oxygen during the lean phases and then like provided during the rich phases. And so this idea is now transferred to the methanation or the methanol synthesis process, where we would like to enhance the decomposition of the CO2 via the oxygen vacancies in the material by introduced by the cerium oxide. Traditional catalysts used are for the methanation process, the nickel aluminum oxide, where aluminum oxide is like the carrier material to stabilize our catalyst. It is treated as inert. For methanol synthesis, we have catalysts usually like copper and on a carrier material composed of zinc oxide and aluminum oxide. And with the novel catalyst development, we would like to have like a nickel cerium oxide catalyst for the methanation and copper cerium oxide for the methanol synthesis process, with a goal achieving the same conversion rates at lower temperatures and pressures, and therefore having a much more economic operation of our Sabatier reactor or methanol synthesis reactor. Yeah, so looking then into like the cerium oxide material. So as said, like the motivation is that you have these kind of oxygen vacancies in your material or in your crystal structure, which allows that the decomposition of the CO2 is much more efficient, and therefore like the formation of methane is also becoming more efficient. But during the research in our group, like there was further development done by developing cerium samarium oxide catalysts, which were showing a better performance, like even better performance by increasing the number of oxygen vacancies in the grid. So therefore, like we further extended the catalyst development towards cerium samarium oxide catalysts. And then finally, you can like impregnate the cerium samarium carrier with the nickel. So you see here, like the nickel is then here adsorbed to the carrier material as the active material in the catalyst. Yeah, just overview about the different measurement and characterization methods available in the catalyst group. So we have several different spectroscopy and microscopy application. We have here like a lead application to characterize the surface of the catalyst. As said, the NAP-XPS is currently in the build-up, so that in the future, like that can also be used for more realistic conditions during the surface characterization. And additionally, like measurement equipment is available for determining the gas composition. The information we can gain from these measurement equipment is then like surface distributions and sizes of the particles, like surface structure and orientation, oxidation state, surface intermediates, chemical information, gas composition, and we can also determine the stability of the catalyst. Yeah, the work that has been done so far, so like study of reference samples to create like a reference data set with nickel aluminum oxide and different kinds of forms like powders or spheres with different sizes. and then like the impregnation, the incipient wetness impregnation of nickel on top of the aluminum oxide. Other investigations was serum oxide and serum samarium oxide nanopowders using either co-precipitation plus impregnation of nickel. And a third method was like then actually the total co-precipitation method, where you have like serum, samarium, nickel, and oxide directly in one co-precipitation process. Structured serum oxide is created by using a hydrothermal method. And the testing procedures used for the pellets and the powders involve like investigation of different pressures, temperatures, and mass flows. Usually we determine the conversion rates. We measure temperature profiles. I will tell a little bit more like on the next slides, because there we have a special temperature applications to get better data for the kinetic model development. And further enhancements will be actually improving the gas concentration measurements along the reactor lengths, and also establishing automated operation of the test bench. So that's also possible to have like a temperature profile programmed in order to do reduction and oxidation automatically. Yeah, here's some results on the surface size using the BET measurement method. So what the group was investigating here was like different compositions of the carrier material and the catalyst, and as well different kind of production methods. So here on the left side, we have the serum oxide, and then the serum samarium oxide with different ratios of serum samarium. In the middle, we have the like the nickel on top of our carrier material with the impregnation method. And on the right side, we have the nickel on top of the carrier material with the the total co-precipitation method. And so what was observed is that with the co-precipitation method, actually we obtain larger surfaces, and that would be beneficial for a higher activity for our catalyst. So therefore, the total co-precipitation method seems to be quite promising in preparation of our catalyst material. Here are some results from the research on the particle size. So we had here some electron microscopic scans of the particles from the total co-precipitation preparation and from the impregnation method. And what we see is that with the total co-precipitation method, actually we are obtaining smaller particles, an average 7.3 nanometer size, while with the impregnation methods, we have an average size of around 18.2 nanometers. So again, here the co-precipitation method seems to perform better because we are leading smaller particles. Another investigation was done like on basically investigating the coverage of the particles with like the nickel on the serum samarium oxide. So again, on the left side, we have the total co-precipitation method, and on the right side, we have the impregnation method. And what was seen from this study is that actually with the total co-precipitation method, we have a much better dispersion of the nickel. So again, yeah, here the total co-precipitation method seems to perform better in comparison to the impregnation, where we see like the nickel here is like quite separated from the serum samarium oxide. So for characterizing the performance of the catalyst, we have in the lab like methane synthesis test bench and the methanol synthesis test bench. I will just focus on the methane synthesis test bench. And the test bench is built up like with mass flow controllers so that the inlet composition can be changed for the reactor. The reactor is installed into oven so that we can control the temperature. And we're measuring pressure, temperature in the system, the volume flow, and as well like the exhaust composition, so that with that data we can actually evaluate the performance of the catalyst. Here are some investigations of the total co-precipitation and impregnation method in the methane synthase reactor. So what we have here on top, the black dash line, is the equilibrium of CO2 under the different temperature conditions. And we see that with the total co-precipitation method, actually we obtaining larger conversion rates. So therefore the co-precipitation is performing better in comparison to the impregnation, which is much lower. At the lower temperatures, we see that the conversion is lower and not close to the equilibrium, since like the kinetic reactions are too slow under those temperature conditions. And looking into the total co-precipitation method, the ratio of serum samarium 2:1 shows the highest activity. So like that is performing the best in that investigation. Yeah, further investigations were done on the effect of different pressures, temperatures, and mixture compositions. One more detailed explanation on the oven. So as said, like the reactor pipe is inside the oven. The oven is here, the green part, so that we control the temperature of our reactor pipe, and the catalyst here is like 10 centimeters of the pipe. And inside we actually have a temperature probe which we can shift so that we can measure the temperature along the length of the reactor. And that is very good, because this information is much more usable for the kinetic model development. And some results, so like here you can actually see like the length of the reactor and the temperature profile. And we see that at the beginning, the temperature is rising. So due to the higher reactivity and the exothermic reaction, temperature increases, while towards the end, like reaction slows down and the temperature is dropping again. In that investigation, the hydrogen CO2 ratio was varied. And what was found is that with an increasing H2 content in the educt, we actually have a larger yield for methane in the exhaust. So yeah, so if you're going for production of methane, higher hydrogen content is beneficial. Also, effect of different forms of the catalyst was investigated, like powders, 1 millimeter and 2 millimeter spheres. And yeah, the differences are quite small. However, like there seems to be a trend like that with the spheres, the 1 millimeter and 2 millimeter, there's a tendency to slightly higher methane yield. Yeah, some details on the model development. So with this experimental data we're obtaining, we are then developing a model for the Sabatier reactor. And this we're distributing into 3 different sections, or 3 different levels. We have the reactor level, the reactor pipe level, and the catalytic surface level. On the reactor level, we are basically just dealing with the convective heat losses and the flow through the overall heat balance of the reactor. In the reactor pipe level, we are looking at the flow through the reactor pipes. So if it's a fixed bed or like with the pellets, you actually have to have here like a porous flow with the pressure loss. And on the catalytic surface level, we are then dealing with the external and internal heat and mass transfer and the surface reactions. So we are modeling the external mass transfer towards the surface of the porous pellet, and then the internal mass transfer to the porous material. And then we're looking into the adsorption, the chemical reaction, and the desorption occurring at the active sites of our catalyst. Yeah, for this surface reaction, we are developing respective reaction mechanisms. In this case, this is a reaction mechanism for nickel on aluminum oxide. since aluminum oxide is inert, it is not included in the reaction mechanism. So we just have here the active species nickel inside, and we have here the adsorption, the desorption, and the surface reactions. And yeah, using the experimental measurements, we are then able to further improve this reaction mechanism. Here is some comparison of experiments with the model performance. So we have here in black the methane, in red the water, in blue the hydrogen, and in green the CO2. The dashed lines highlight the equilibrium at the different temperatures, while the thick lines are the kinetic simulations, and the symbols are the experiments. And at the low temperature range, we see that the conversion rate of H2 and CO2 is very low because kinetics are too slow. And with increasing temperature around 630, we are reaching equilibrium. So kinetics get fast enough in order to convert CO2 and H2. And the agreement overall of the model with the experiments is quite good. Yeah, so the idea is that with this, with a Sabatier reactor model, we can do now further developments regarding implementing it into a power to X to power digital twin, which we can use to simulate the whole energy system and optimize the energy system, and yeah, use it as a digital twin. So we can connect it with the real process, use it to do some predictions on optimum operating conditions, and then feed that information back to the process to operate it under ideal conditions. So that is like a long-term idea for the development. Yeah, now I will come to the last aspect of the today's seminar presentation, which deals with the oxyfuel combustion for heat and power generation. So with the oxyfuel combustion, so what we're doing is when we compare it to the methane air combustion, we're actually taking out the nitrogen out of the equation. So means we only have methane and oxygen in our mixture. And the advantage of this approach is, first off, we have a NOx-free combustion. Further, we are yielding higher burning velocities because we do not have the effect of the heat capacity of the nitrogen. And third is we having exhaust gas with a high concentration of CO2, which is an advantage for the CO2 separation in the exhaust. Disadvantages, especially like for the combustion engine, is the high combustion temperatures. So the materials of a gas engine are usually not capable of bearing these high temperatures for a long time. So you would damage the engine much faster. And a second point is that the operation with oxygen also requires increased safety demands, especially with concentrations above 30% in like 30 volume percent or pressures above 5 bar. We actually have to use different materials and have to do additional safety measures to avoid explosions in the systems. Yeah, so what I'm going to show today in the investigations are the studies we did with our numerical model in order to better understand the oxyfuel combustion in our engine, so that we can derive some strategies for the build up of the oxyfuel test bench. So in that investigation, we are using D-type reaction mechanisms to describe the oxidation of the fuel. We're having our 1D premix flame simulation tools to calculate the laminar flame speed for different pressure, temperature, and dilution conditions. And then we're using actually the information like the 1D flame solution and the reaction mechanisms to perform like the CFD calculations of our engine. Some studies we did for the laminar flame speed was to see, like, first of all, like how is the laminar burning velocity for methane oxygen mixtures. Therefore, we used like experiments from Mus Monetas, and we compared different kinetic models to see the performance. And yeah, here we compared like a mechanism from DTU, from Polemi, from Schrechter, and from Fu et al. First off, here, these are lean conditions we are investigating. Overall, the trend looks okay for the models. However, at higher temperatures and pressures, there's a tendency for underpredicting the flame speed. And so might be that like we maybe need additional experiments, maybe also different kind of experimental devices to further investigate that, but it might be that some further model development might be necessary on the lean side. From the performance of the kinetic models, usually performance quite similar, while smaller differences are observed, like here, for example, for the DTU in the CH2O chemistry, and like in the HCO reactions, which show different sensitivities for the reaction mechanisms. On the stoichiometric conditions, generally the flame speed is increasing. The models showing like tendency for underpredicting, while the trend looks okay for increasing temperature and pressure. And when we go to the ridge conditions, wrong direction, we see that there's a tendency for the models now to overpredict the experiments. Flame speed is generally decreasing for the ridge conditions. And we see a good agreement of the Fu et al. Mechanism under these conditions, and as well, like the DTU and Polemi are performing quite well. While the Schrechter mechanism shows a tendency, especially at high temperatures and high pressures, to underpredict the experiments. So I guess therefore maybe like additional experiments, maybe also with different devices, would be helpful in further evaluating the kinetic models under oxyfuel conditions. Yeah, just a little bit more details on the CFD model we are using. So like it's a two-port engine with a pre-chamber system that we're currently using and a hemispheric bowl shape. And so we validated the model for methane air combustion. So here are some LES results we simulations we conducted and found a good match. We're comparing here like the simulated dashed line to the full lines from the experiment. And we used here the maximum minimum pressure and the average pressure of the measurements in order to like get an idea about the fluctuation. And the simulation is within that range of the experiment. What we then do is actually we convert the methane air case into the methane oxygen, so we can investigate the methane oxygen. And what we see is, and what we expected is that with the methane oxygen, the combustion is significantly faster. So we have here the different crank angle times of our engine cycle, and we see that the methane oxygen combustion has already nearly completed the combustion at 5-degree crank angle, while the methane air is still in the beginning at 10 crank angle degree. And due to this fast combustion, we have a much stronger pressure gradient. And we also see that the maximum pressure and temperature are increased quite significantly compared to the methane air. As you can remember, when I was showing the chemical equations for the methane air and methane oxygen, like with taking out the nitrogen out of the mixture, you're actually also changing the fraction of methane in the total mixture when it's stoichiometric. So means if I'm not changing anything on the inlet pressure and inlet temperature of my engine, I have the same mass inside. Due to that I take out nitrogen, I actually have a higher fraction of methane in the total mixture, which lead to that I also have more energy in the system. And that is also one reason why the power for the methane oxygen system is higher compared to the methane air. So we have here like 3 times more power output with the methane oxygen combustion. Yeah, so some studies we did. So like we then investigate, okay, what is happening if we have the same fraction of methane in the mixture? When we do that for the methane oxygen combustion, actually you would need to lean out the mixture, and that is giving you a lambda of 6.4, which is at the flammability limit actually of a methane oxygen flame. And what we see is that with the methane oxygen, first off, like the significant increase, while when we dilute the mixture, we actually we actually decreasing the maximum cylinder pressure, and due to the lower flame speed and the lower energy in the system. From the emissions, we see that with the methane oxygen combustion, we having higher concentration of CO and hydrogen in the exhaust. You can sit there. And so that is like what we see under these high temperatures. Actually, we're starting to form a synthesis gas. And for the leaner conditions, we see that actually the CO concentration stays the same, while the hydrogen is reduced. Yeah, another method to control the temperature in the methane oxygen combustion would be dilution. Therefore, we investigated dilution with CO2 and with water. Well, for the water, we excluded the effect from the water vaporization for now. And we see that first off, we had here in black the methane air flame speed, and in this like purple color, we have the methane oxygen flame speed. And with increasing amount of CO2, we can reduce the flame speed as expected, and around 50% of CO2, we obtaining the same flame speed as the methane air mixture. While for water, we see that we need around 63% of water in order to achieve the same flame speed as the methane air mixture. When we apply that to the engine calculation, we see like the significant reduction of the peak cylinder pressure. Also, combustion is delayed and temperature is also reduced. In the compression stroke, we see a difference between CO2 and H2O dilution. So like CO2 yields a smaller compression pressure and temperature. While during the combustion and during the end of combustion, we see that with the water, we actually have a lower temperature during the exhaust stroke. From the emission point of view, there is like a opposed trend. So means like with CO2 dilution, we have tendency to have more CO and less H2 in the exhaust, while with water, we have more H2 and less CO in the exhaust. Yeah, the last aspect that we looked into was changing actually the composition of the fuel we are using. So you could do that by operating the Sabatier reactor under different conditions. So what I'm showing here is actually operation under 1 bar and 350 degrees Celsius, and another case under 30 bar and 300 degrees Celsius. And different ratios of H2 to CO2. So one with a stoichiometric ratio and one with excess of CO2. And what we see for the, first of all, what we see with increasing pressure is that you yield more methane in the mixture. So with lower pressures, actually, the ratio of hydrogen is much larger. While when you go to a higher pressure, you're shifting towards methane. So the fraction of methane becomes larger. With the increase of CO2 in the initial mixture, of course, we are increasing then also the CO2 content in the exhaust gas. And that we can see in the lower heating value and as well in the laminar burning velocity. So in black is again natural gas air. And then in red, that is the methane oxygen case. And then blue is the stoichiometric ratio and green is the excess of CO2. With the case of a stoichiometric ratio and lower pressure of the Sabatier reactor, we actually slightly enhance the flame speed, even though that the lower heating value is decreased. The reason is we have a higher fraction of hydrogen in the mixture, while with increasing fraction of CO2, you're decreasing the laminar flame speed and the lower heating value as well. For the higher pressures, we actually see that the flame speed is slightly lower because we are reducing the content of hydrogen in the exhaust mixture. Effect on the engine is then that with the stoichiometric ratio at the 1 bar pressure, we slightly burning faster at the beginning, while the peak pressure is reduced because our lower heating value is reduced. And for the excess of CO2 in the mixture of the Sabatier reactor, we see that the combustion is delayed due to the lower flame speed, and also the maximum pressure is reduced and totally like the energy is reduced because a lower heating value of the synthesis gas is lower. From an emission point of view, actually we see that with the stoichiometric ratio, there's not a big change, while with the excess of CO2, there is like a trend for having less CO and H2 in the exhaust. Yeah, summarizing the presentation from today. So we have developed this novel nickel cerium samarium oxide catalyst in the ESC catalyst group, which is very promising, shows high activity at lower reactor temperatures, and that will be further researched and developed in the coming months. We are working on developing the methane synthesis reactor for our energy system prototypes, so to further understand the performance of such a system. From the Oxyfuel combustion, we investigated like different mechanisms to control the temperature, while for the prototype build up, we are first planning to using CO2 dilution for temperature control. And then we hope that with the Oxyfuel Testbench, we will ready to be in operation in beginning of next year, so that we can test the system and start first experimental campaigns. Yeah, at the end, I would like to acknowledge that this project is funded by the German government and the Brandenburg and the region of Brandenburg. Here are my contact details in case you're interested in cooperations or just having some exchange on certain topics. Feel free to reach out. Our group is very happy to always start new cooperations. And with that, I finalize my talk for today. And yeah, if there are any questions from your side, feel free to ask.
Thank you very much, Tim, for this very nice talk. I open the discussion for questions. I don't know if there is any questions from the people online. If you don't want to unmute yourself, you can actually ask your questions in the chat, and I will read it to Tim. While you think about it, I have actually a couple of questions myself. So when you talk about these, heterogeneous reaction mechanisms, I was wondering if you see any opportunity for machine learning approaches to help you discover reactions and build mechanisms for conditions where you don't have a solid knowledge of the reaction mechanisms to start with.
Mm-hmm. So like for development or discovery of new reactions, I've yet not thought about that a lot. What we have thought about application of a machine learning algorithm is, for example, like this kind of additional data that we have, like the thermo data, for example, it could be used for, or another aspect would also be to make the whole model faster. So like such a simulation, a 1D simulation with a detailed reaction mechanism takes some time. And if you want to apply that to a system optimization, it is not feasible. You cannot incorporate it. So what we want to do is, how can we actually derive like AI model from this 1D model that can be used for that? So for example, how can we put this detailed reaction mechanism into a machine learning model? And that makes then the whole process simulation faster. We have already started working on that in some aspects, like with Gaussian processes, for example, and deep learning model. But still, we see like there's a lot of way to improvement. So therefore, I think in that direction, like making a meta model out of the detailed model, like that is currently a high interest. How to do that,
Yes, makes sense, of course. Thank you. I don't know if there are questions. There is a Salvatore who has a question. Yeah.
Yeah. Hello. Hello again. Thank you for your very nice talk. I have a curiosity about the Syria, this serial metal, and its availability in the case if you have already investigated some sort, the feasibility, if you have really done a feasibility study, what's the availability of Syria in case you want to scale up the process that you're currently investigating.
So for the Syria, I already mentioned, so that's quite common, be used in the three-way catalyst. So that means from this point of view, the cerium oxide is already like used on an industrial scale. And I think with the samarium, and maybe my colleague can correct me, but I think with the samarium is also not a huge issue. It's not very expensive material, so therefore, like such a cerium samarium oxide catalyst can be also economically produced on an industrial scale.
Okay, thank you. Yeah, I'm sorry if I missed that. I guess, yeah, my other question would have been about the simulation, the cost of the simulations, but you already mentioned that it's important to have a meta model in view of what you said about creating a digital twin. So I'm guessing the simulations, especially if you look at the particle level, are quite expensive. So
exactly.
So if you want to, if you're looking to build a digital twin, you need some, reduce order modeling and
exactly.
company.
And the current challenges, as I said, like the current challenges we have is actually how can we effectively like model this kind of process in a meta model, you know, like because we are looking for a meta model that can also predict the transient behavior, you know, so that what is happening if the synthesis reactor is only operated until 50% due to some reasons, it's not fully converting in a dynamic system. That can maybe happen because you have like a start of the system, you have a shutdown of the system, and that could lead to conditions where the chemical conversion is just not complete. And so therefore we are looking for meta models which can also predict this kind of transient behavior. And there's a question like, how do you reflect this kind of transient behavior? Like my idea is doing that with the reaction progress variable approach. But what is a suitable reaction progress variable for Sabatier reactors? So there are a lot of questions currently to be answered, you know.
Okay, yeah, that's very interesting topic. Thank you. Thanks a lot.
Yeah, you're welcome.
I don't know if there are other questions. Otherwise, team, thank you again very much. And really, this was a very insightful talk. And I thank also the people who are present and to the next event of the series. Thank you. Thank you. Thank you all.
Thank you very much. Have a nice time. Bye, guys.
Bye-bye.